Hello, everyone. My name is Eidels, and this is a pre-recorded presentation for the annual meeting of the Society for Mathematical Psychology 2020. The project I'll be talking about investigates the processing architecture in memory intersection problems. And this is a collaborative work with Psyc Howard and Bianca Belewski from the University of Newcastle, Australia, and Simon Dennis from the University of Melbourne. First, let us understand what is a memory intersection problem. Suppose I ask you to think about a movie with Robin Williams. Naturally, a long list of movies could come to your mind, and you can't quite tell which specific movie I have been thinking about. To help you, I need to provide you with another cue, and it is the combination of the two cues that could lead to the single solution I have been considering, Mrs. Doubtfire. In visual form, we can present this as a Venn diagram, where each cue leads to a number of solutions, and it is the intersection or the shared area of the two circles that provides with a single solution. Memory intersections have been defined and studied elsewhere. Smith, Huber, and Val called a process of memory retrieval in which two or more cues, so-called constraints, are required to prompt a specific memory or target response. You could ask why this is important, and if I were Simon Dennis, I would say everything in intersection. And Simon is not off the mark. Intersection problems are quite ubiquitous. When making dinner given a limited set of ingredients, one needs to consider how the different ingredients they might have in their kitchen can be used together to provide a single recipe. Memory retrieval of everyday facts require intersections, as do crossword puzzles, Sudoku, and also riddles in popular cultures, such as those posed by Bilbo and Gollum to each other. It is also interesting to know that memory intersection could be unique to human intelligence, and that as of today, most artificial intelligence algorithms cannot solve intersection problems yet. So our question was this: are multiple constraints considered in parallel or in serial when identifying an intersection of multiple cues to retrieve a memory? So in the remaining of the presentation, I will introduce you the challenges of studying processing of multiple cues and constraints. I'll propose a way to overcome those challenges using a methodology called systems factorial technology. I will present you with two experiments using recall and recognition frameworks, and finally some conclusion and discussion. How do we process multiple cues? Well, one way to do this is to consider two cues in parallel at the same time. Yet an alternative would be to consider one cue and only then to process the other cue in what we call serial processing. In addition to the serial and parallel nature of processing, we can ask how much information does one need to process before making a decision. A minimum time, sometimes called self-terminating or decision rule, suggests that we could stop processing and make a decision after one source of information had been processed. Whereas a maximum time, exhaustive or end rule, suggests we must process all the cues before making a decision. So here's an example of how a parallel intersection search might look like if we assume a simple spreading activation model when searching for a piece of memory. If I activate the two cues at the same time, as I do now, activation would spread concurrently to all related nodes, and a single node, which is the intersection, will be activated to indicate that Mrs. Doubtfire is the correct movie. Recent work by Smith and colleague used the remote association test to study how people solve multiply constrained problems. They suggested that participants produce guesses based on only one of three cues at a time. However, telling apart serial and parallel processes is not a trivial feat at all. First of all, because of the sequential presentation of cues. That is, if cues are presented one after the other, we can't quite tell whether the actual processing would have been any different in serial. And the second challenge is the serial parallel model mimicry. Now, if cues are presented in serial, say first a question as to a movie with Robin Williams, then activation from that cue would spread, but no single solution can be identified yet. It is only with the presentation of the second cue that a single node can be concurrently activated by the two cues. And again, this might look like a serial process for us, but it is driven or motivated by the fact that the cues were not available at the same time. So the current study tries to address those two challenges. We present a method that, based on analysis of response time distributions, allows us to uncover mechanism underlying the processing of multiple intersection cues, and specifically the question of serial and parallel processing. We show that we can eliminate the confounding effects of sequential cue presentation and that the method is immune to model mimicry. Much of the work on serial parallel model mimicry had been driven by Jim Townsend from Indiana University. A classic example is that of visual search, where for many years it was believed that the slope of the search function can be mapped uniquely to serial or parallel processes. Jim's work suggested that serial and parallel models can generate similarly looking slopes of the function. Following this diagnosis, Townsend and his colleagues developed a remedy, system factorial technology, which is a method that can overcome those limitations. In a nutshell, in system factorial technology, we manipulate the strength of two cues. The strength can be high or low, and we then calculate a contrast of survivor functions. This contrast, the survivor interaction contrast, or SIC for short, is unique to each and every model. Now, to apply SFT to memory intersection, we need to selectively influence each one of the cues. We need to make each of the cues either high or low in strength. And we did so by manipulating the associative strength of the cues to the target words. Just to give you a sense of the method that we've used, in two experiments, which I shall refer to as recall, two cues were presented on the screen, say hive and sting. They were then removed, and the participants had to indicate which word is related to both cues. In experiment 1, they did so by typing, and in experiment 2, using a vocal response. In another set of experiments, experiments 3A and 3B, which we call recognition tasks, the participants were again presented with two cues, except that this time we have also presented them with a target item, and they had to indicate whether this word is related to both cues or not by a key press. In all instances, we measure the response times and estimate response time distributions. The manipulation of cue strength was based on the Dan et al. Free association norms, whereby the cue strength is defined by the probability of a specific cue to be associated with a target word. Out of the corpus of words, we've selected words that fell into a band of low and high probabilities. So for example, to illustrate, if we have the target word B, then two cues which are highly related or strongly predicting this target would be hive and sting, whereas in the low-low condition, two cues that could have a low level of connection would be bear and flower. Systems factorial technology is based on a factorial design, and this can be achieved using the two cues if we manipulate each and every cue, resulting in a combination of high and low level for the top cue, high and low level for the lower cue, resulting in 4 overall conditions, which we denote high, 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 low, low, high, and low, low. We estimate survival functions for each one of these conditions, and we then plug them together to calculate the survivor interaction contrast. each participant needs to produce quite a few tries, and for these participants sat for more than an hour, observing more than 700 tries and responding to each and every one. Overall, we had 118 participants across the different experiments. So before we go on to see the results, record the model predictions. On the left-hand side, we see an illustration of survival functions, and on the right-hand side, when putting those survival functions together to produce the SIC, we can see that parallel and serial model, coupled with the or and decision rules, predict a unique signature for each model. That signature could be an all negative function, an all positive function, a flat line, or a function that starts negative and then tends to be positive. In this figure, I show you an example data set for one participant, participant 4, whereby the function on the top right-hand side, marked in blue, is negative for all time t. Compare that with the predictions of the models presented at the bottom panels, and you can see that this signature best fits the description of the parallel end function. So we've repeated this analysis for each and every participant. And after doing so, we discovered the following pattern. To understand this figure, note that the y-axis denotes the proportion of subjects showing a particular processing strategy, either serial or parallel. The blue color represents parallel processes, and the orange color marks participants who had shown a serial processing architecture. And as you can see, there was an overwhelming majority of participants that had used a parallel strategy to process two queues in order to find the intersection. You can also see that although overall there was an advantage to parallel processing strategy, this advantage was larger in the recall experiments on the left-hand side, whereas on the right-hand side, the recognition experiments has a slightly larger proportion of the orange area marking serial processes. So our goal was to meet some challenges concerning the investigation of intersection problems. We hope we have been able to overcome the issue of model mimicry by using SFT. SFT is robust and resilient to the mimicry issues. Manipulating the Q strength could be tricky, but had been proven successful after many failed attempts before. The Qs in our study were presented simultaneously, and this had helped us overcome the sequential nature of presenting Qs that potentially had limited previous studies. In conclusion then, this is the first successful demonstration of SFT, systems factorial technology, to study memory intersection, and a successful manipulation of Q strength necessary to propel the application of SFT. There were individual differences in search strategy, but overall most signatures, most participants seems to process information in a parallel and exhaustive manner. Interestingly, there was a high proportion of parallel processing in recall, but a slightly lower proportion in the recognition experiments, and we are not quite sure why. If you'd like to read more a little bit about this study, it had been recently accepted to publication in the journal Cognition. Thank you very much for your time and attention.